welcome back to General Chemistry 2. My name is Daniel, and in this video we're going to start looking at the structure of solids. That is, how the atoms and molecules are organized in the crystal structure of certain solids. So we should begin by once again defining a solid. We went into it very briefly in the very beginning of the course. So for our purposes, a solid is just a material where its atoms are in essentially fixed positions. We know that's opposed to a liquid where the molecules or atoms are freely flowing, or a gas where that's even more so. So there's two main categories of solids. The first one is what's called amorphous solids. These are solids that don't have any kind of organized structure. They're very disordered, don't have any kind of repeating measurable structure. We'll get more into those in the second part of the video for this chapter. For this video, we're going to focus primarily on crystalline solids, and that's just the opposite of an amorphous solid. So crystalline solids have a very regular kind of arrangement, a repeating unit of structure. And then there are also categories within the crystalline solids. There's ionic solids, metallic solids, network atomic solids, and molecular solids. We'll get more into depth about the distinction between those, once again, in part 2 of this unit. Today, though, we're going to primarily talk about the first two, the structure of ionic solids and metallic solids. And we're going to see what is the repeating unit that characterizes these structures, how do we determine these structures, and then we'll do calculations using those structural patterns. A crystalline solid has a repeating unit. We say that it has something called a crystal lattice. That is the three-dimensional array of how the atoms, molecules, what have you, are arranged in space. We can characterize this by something that's known as the unit cell. So here's just a demonstration of the lattice. It's just this three-dimensional system of points. You see that we have some ions in the corners of this arbitrary cube, other ones with the lithium on the sides. And so we can see how this 3D array makes up the structure of this solid. And we can see that there is this repeating structure. This repeating structure is what's known as the unit cell. So if you look at this diagram here, we'll see that the red highlighted box is one of our unit cells. And then the unit cell for the entire solid just repeats throughout the structure of the solid, and that's what gives it its crystalline repeating pattern. What we can say the unit cell is just the smallest array of repeating atoms, meaning that obviously everything in this entire structure is repeating, but this red cube is the smallest repeating structure. It's like, let's say we had ABC, ABC, ABC. Obviously the whole thing is repeating, but we call this first section our unit cell because it's the smallest unit that repeats. In the same way, we define the unit cell. Let's see how do we determine what is the unit cell of a solid? What is the position of the different atoms or molecules or ions? We do that through a technique known as X-ray diffraction. So what happens here is first we have X-rays shined on some kind of material, whether it be a powder, a crystalline solid, what have you. So the reason we use X-rays is because the wavelength of X-rays, their lambda, is similar to the spacing in between layers of a solid, which you see here by this factor D. So we can say that the wavelength is similar to the separation between layers in a solid. What happens then is that diffraction occurs when the X-rays hit the layer of the solid. You can see that here. One ray reflects off the top layer, another ray that's parallel goes down, hits the second layer. And so what happens then is that there's an extra distance that the second wave travels. You can tell that's going to be based on the separation D, the incident angle here, just applications of trigonometry. But what we can say is ultimately it's going to move an extra distance. So what we can say then is that certain diffractions are going to have either constructive or destructive interference. We see in this picture in particular, when these two rays are incident with one another, meaning that they're in the same kind of phase, because you can see their crests are matching. With this extra distance ray 2 travels, it comes out also in the same phase, which we can see over here. That's going to lead to constructive interference, which means the signal is amplified. If, on the other hand, that second wave moved in a certain distance that resulted in something like this, where you see everything is out of phase, that would be destructive interference. And that would mean that there's less, weaker or no signal. So what this results in is a pattern that looks something like this on the right. This is the X-ray diffraction pattern for cubic silicon carbide. So what we see is that there's certain what we call diffraction peaks here. Those are the areas where there was constructive interference at these angles of incidence, at these what's called 2 theta levels. Theta just being the angle at which the X-ray hits the solid. So you can change that with your device. So we see at certain angles, we're going to have constructive interference, like we would have, let's say, over at this peak. On the other hand, we'll have also some areas of destructive interference, where there's minimal to no signal. And like we said, the reason for that is because of that extra distance that's traveled by the second wave. So this leads us to an equation that describes this behavior, and it's called the Bragg equation. What we say is that n times the wavelength of the X-rays equals 2d sine theta. This is the extra distance traveled by any kind of wave that's going down beneath the surface, meaning that we can have n equal to some arbitrary number, n equals 1, 2, 3, so on and so forth. Just describing something like this system here, we'd have 3 over here, something like that. So the wavelengths we have the same wavelength for all of those, and then the extra distance traveled by them is equal to 2d sine theta, which you find through some trigonometry that it's I'm not going to derive here. But d is just a separation between 2 layers, as you see here. And then the theta in the sine is just like we said, the angle at which the X-rays are hitting the surface, which by also trigonometry transfers down here. So that's how we can determine the structure of unit cells. Then you'd use some advanced mathematics or a computer equation, computer program to analyze this data, and it would eventually come up with a model for the structure of the solid. And the result of that looks something like this. We have a few different kinds of unit cells that we can have, all based on differences in 2 things. We can have differences in the length of each side of these unit cells, meaning we have something like length A, B, C, length, width, and height, something like that. And we can also have a difference in angles. So for example, if we look, the most basic unit cell we see here is the cubic one, the first one. That's because A equals B equals C, and the angles are equal to 90 degrees. So this is just the simplest one, a cube. If we get more advanced or more complicated unit cells, we start having things not equal to each other. For example, if we go to the orthorhombic over here, we see that the angles are still 90 degrees, but now the lengths of each side are different. So that means A isn't equal to B, isn't equal to C. And then we get even more complicated. We can go, let's say, to triclinic down here, the most disordered one, where nothing's equal to each other. All the edges are different, all the angles are different.